Hey everyone, and welcome. So, same name, different tasks. If you've spent any time in the world of software development, especially object-oriented programming or OOP, you already know there are two legendary concepts that sound so incredibly similar they literally trip everyone up. I'm talking about method overloading and method overriding. Look, let's be real. Back in our early coding days, we all mix these two up. Am I right? Well, today we are diving deep into this exact topic to clear up the confusion once and for all. Here's our roadmap for this explainer. We'll start by looking at these two concepts that share one confusingly similar name. Then we'll build a really strong intuitive mental model before diving into the strict technical rules. After that, we'll look at some real-life code examples, and finally, we'll wrap things up by comparing static and dynamic polymorphism. All right, section 1. Two concepts, one name. Overload versus override. So as developers, we constantly get overloading and overriding confused, mainly because, linguistically, they sound almost exactly the same. But before we even look at a single line of code, I want you to lock this mental model into your brain. Think of overloading as having a single, trusty power tool, but you swap out multiple different attachments depending on the job. The tool itself is the same, just the inputs change. Overriding, on the other hand, is like tossing that original tool aside and picking up a completely upgraded, custom-built version tailored specifically for a brand new user. Same original purpose, completely different execution. Section 2, intuitive explanation. What's the actual difference here? Okay, imagine you're ordering at a restaurant. You walk in, look at the waiter, and say, "I'd like to order." Now, sometimes you might just order a meal. Other times you might order a meal and a drink. Notice how the fundamental action, the name of the action, ordering, stays exactly the same. But because the inputs you provided changed, what actually shows up at your table changes too. That right there, that is method overloading. It's the exact same action name, just handling different inputs. Now, let's instantly contrast that with overriding. Think about animals. As a broad parent concept, a generic animal makes a sound, right? That's just a generic inherited behavior. But when a specific dog walks onto the scene, it inherits that basic make a sound action, but it completely overrides it to bark. It customizes it entirely. So with overriding, you take a basic inherited action from a parent, but you completely rewrite it to fit the specific entity performing that action. Moving on to section 3, technical details and rules. Time to look at the strict rules of the game. Now that we've got our mental model down, let's get into the nitty-gritty technical stuff. If you are overloading a method, here is your golden rule. You must be in the exact same class. You must use the exact same method name. But, and this is a massive but, you must have different parameters. That could mean a different number of parameters, different data types, or even a different order. You're creating variety, but you're staying within the exact same class boundaries. Remember this, same class, different parameters. And on the flip side, we have the rules for overriding, which are practically the exact opposite. First off, overriding absolutely requires inheritance. It happens between two different classes, a parent and a child. Your method name still has to be the exact same. But like overloading, your parameters must also be the exact same. Same method name, exact same inputs. The outer shell is identical, but the actual work happening inside the method is completely rewritten. Now, I want to pause and highlight a massive best practice here, the @override annotation. When you're replacing a parent class method in your child class, you don't technically have to use this tag, but you absolutely 100% should. Why? Well, it explicitly tells the compiler, hey, I intend to override a parent method right here. If you make a typo or mess up the parameters, instead of failing silently and causing a nasty bug later, the compiler will instantly throw an error. It's basically a safety net for your code. But wait, when you override a method, is the original parent code just gone forever? Not at all. This is where the super keyword swoops in to save the day. Overriding doesn't mean you have to destroy the original behavior. The super keyword acts like a bridge, allowing your child class to reach back and call the parent's original method. You can actually run the parent's logic first and then stack your own custom logic right on top of it. It's super powerful. Pun intended. All right, quick pause. I want to ask you a question, and honestly, this is a classic trap in software interviews and a huge source of bugs. If you keep the exact same method name and the exact same parameters, but you only change the return type, is that considered method overloading? No way. Absolutely not. Changing just the return type does not trigger overloading. In fact, it's just going to throw a nasty compiler error. See, the system running your code only looks at the method's name and the parameters you're passing in. If both of those are identical, the compiler gets totally confused. It has no idea which version of the method to call. For overloading to work, the parameter list has to change. The return type alone just doesn't cut it. Section 4. Real-life examples. Let's see this in actual code scenarios. Let's ground all these rules with a practical example. Imagine a banking system using overloading. Method number 1 is deposit money, and it just takes one parameter, the amount. Now, method number 2 has the exact same name, deposit money, but it takes the amount and a description. The logic here is crystal clear, right? Sometimes a user just wants to drop off cash. Other times, they want to drop off cash and leave a note saying rent money. It's the exact same logical action, just handling different levels of input detail. Now let's look at an overriding example using our animal concept. We have a parent animal class, and its method simply returns the string making sound. Then we create a child class called cat that inherits from animal. But our cat class doesn't want to just make some generic sound, so it overrides that method using the exact same name and the exact same parameters and forces it to return meow instead. The generic behavior we inherited was completely replaced with something highly specific to the child class. Section 5, Static and Dynamic Polymorphism. This is where we look under the hood. The crucial thing to grasp here isn't just how we write the code, but how the machine actually processes it. Overloading and overriding are basically two sides of the polymorphism coin. Side 1 is static polymorphism, also known as compile-time polymorphism. Why is it static? Well, because overloading relies on having distinct parameters, the compiler looks at your code and knows exactly which method to run before the program even starts. The decision is locked in statically during compile time. Side 2 is dynamic polymorphism or runtime polymorphism, and overriding is the absolute prime example of this. With overriding, the parent and the child have methods with the exact same name and the exact same parameters. Because of this, the system actually has to wait until the program is actively running to see which specific object, like a cat or a dog, is making the call. Only then does it dynamically decide which version of the method to execute. The decision happens on the fly, at runtime. To bring this whole explainer together, let's review this comparison matrix. It's basically your ultimate cheat sheet. For the class, overloading happens in the same class, while overriding requires inheritance. For parameters, overloading must be different. Overriding must be the exact same. For polymorphism, overloading is static. Overriding is dynamic. And finally, for resolution time, overloading gets sorted out at compile time, while overriding is resolved at runtime. Lock this table in your memory. It's an absolutely crucial reference for your future design decisions. As we wrap up, I want to leave you with a question to challenge your architectural thinking on your next coding project. When you're designing a system, do you need the flexibility of a single action adapting to different inputs? Or do you need to take an inherited behavior and completely rewrite it from scratch for a brand new entity? Answering that question will instantly tell you which of these two powerful techniques to use. Thanks so much for joining me on this explainer, and I'll see you in the next one.